Okay, so here's what we were talking about last time. We were talking about optimization. And remember, the big idea with optimization is it's a lot like single variable optimization. Multivariable optimization, pretty much the same idea. We're looking now, of course, the big difference is we're looking at a function whose domain is not one-dimensional, so thus multiple variables, right? And the domain then is not an interval. The domain is a subset of, well, Rn. And so wherever you might happen to be, there's lots of different directions in which you can go, right? We can't just talk about the derivative, as in like a partial derivative or something. So the idea is, again, process of elimination. We look at a point, and the way I decide if that point there, or a way that I can address the question of whether that may or may not be a maximum, is ask, can I eliminate it? Right? And easy observation, if the function's differentiable and if the gradient is not zero, you have right there a way of eliminating that as a possible maximum. Right? It's got a gradient. It's got a well-defined direction in which you can go that the function is increasing. Right? It's not a maximum. The function's not as big as possible there. It's still getting bigger. Right? So this process of elimination is the main tool that we use, but we of course in reality, in practice, we tend to use it in reverse. Namely, we look at where it fails. You know, the actual tool that we have finds not maxes. We're not looking for not maxes. We're looking for maxes, right? So what we're interested in is where our process of elimination fails. We're looking at points where the function fails to be differentiable, and thus the above argument doesn't apply. Points where the gradient is zero, in which case there is no direction that the function, that we know the function's increasing, and there's just, again, the argument fails, right? We can't rule it out as a possible maximum. We don't know what's going on there. So we give it a name. We call it a critical point. We promise to come back and think about it later. Right? Is basically the idea. So do keep in mind, I cannot emphasize enough, one of the most common misunderstandings about this sort of optimization is to think that when you found a critical point, you have in fact found a max or maybe a min. It's got to be a max or a min. This is absolutely not true, right? The whole point to critical points is that we don't know. We have no idea. Our one little simple-minded process of elimination strategy fails, and we're back to square one. We know nothing. Okay, so there are lots of possibilities other than extrema. Yeah, sure, max. Turn this upside down, it's a min, right? Those are all possibilities, but it's also possible to be a saddle, aka Pringle, right? Or it could be a shoulder point, or a monkey saddle like we were talking about on Monday. Lots of different possibilities. Okay. All right, we did an example. This is the last thing that we did last time, as I recall, was we looked at this function here, and we looked for critical points, and we found two critical points of this function. Right. Okay, so there are lots of possibilities, though, as to what these could be. Right, and the mere fact that they're critical points doesn't really help us very much. In fact, we considered some sort of various arguments that pretty quickly demonstrated that neither of these is a max and neither of these is a min. Okay, so I want to show you a little bit harder of an example here, just to point out that the algebra does get a little sticky sometimes. Multivariable algebra is hard. It just is. It's not as simple as single variable algebra that you saw in high school. And sometimes bad things happen. Often bad things happen. Right. So here's a simple example. Suppose we had some function. We took the gradient, and we got this as our gradient, and we set that equal to 0. And okay, then solve. Whatever. That's the easy part. Is just solve for the x and y. And I claim that this is tricky. This is not at all immediately clear how you would do this, because there's a temptation to look at this. It says x squared minus y squared is 0. A lot of students would just immediately go to x equals y. I mean, if x squared is equal to y squared, let's just take the square root of both sides of the equation, and now x equals y. And it's not true. Right? My experience has been, and by the way, both as an instructor of former high school students and also as a former high school student, that high schools sweep a lot of stuff under the rug in algebra. They very often, and I don't know your personal experiences, of course, right? But very often, my high school experience included, high schools just say, well, man, absolute values are confusing, and pluses and minuses are confusing. So let's just not worry about that, right? And the teachers and the students, it's sort of win-win conspiracy to ignore sticky issues, right? And so a lot of students get to a class like this one and are not only unsure of how to deal with this, but also highly comfortable with just ignoring it. This is not good. Okay, so here's in this case, how do you deal with this situation of x squared equal to y squared? Well, there are, in fact, easily seen to be two possibilities. It could be that x is equal to y, or it could be that x is equal to negative y. We don't know, right? You can't just say, definitely that one. And likewise, you cannot just say definitely that one. It just, it doesn't work, right? So we have to consider two separate cases. And, we're responsible for both of them. So, one at a time, let's start with x equals y as a possibility and then see what that tells us. If it were to be the case that x is equal to y, what else could I conclude? Okay, well, so if x is equal to y, stick that into there. And we need both components of the vector to be 0. If x is equal to y, that means that, I can plug in for the x. It's y, right? And that gives us this equation for y, which you can then solve and get these two possible values of y, which you will see there and there. Having solved for y, then of course you can also then solve for x, which you see there and there. Everybody on board? Okay. All right, so that's case one, right? It is possible, we agreed, that maybe x is equal to y, and we've considered that case, and that has given rise to two critical points. But the other possibility is that x could just as easily be equal to negative y, and if that's the case, then you get a different little bit of algebra here. Let me give myself some space. If x is equal to negative y, and again, just plug it in. X equals negative y. Plug that in right there. And now you have this algebra for y. It's different algebra. Thus, unsurprisingly, it gives you different values of y. Therefore, different critical points. Right? Those values of y, how do you get the x? Well, keep in mind, you're plugging those values of y into this different scenario that you're considering for x and y's relationship. So you get those values of x determined in a different way from the previous case. Right, so anyway, there you go. That's how that algebra works. Notice that we get now then two sets of critical points. Conveniently, this one's already equal to that one. I sort of found that point twice. Whatever. Right. So grand total, then we have 3 critical points to consider for this function. Okay, so heads up on the algebra, right? Don't move too fast and loose with the algebra, and square root of a square. Oh, that's the number, right? Just sort of blow on by, like a lot of us were not only allowed but encouraged to do in high schools. Okay, all right. Okay, so what do you do with these critical points? How do you know what's going on at a critical point? At which momentarily a critical point is a point where we don't know what to do. So how do we fill in a blank? How can we sort of resolve that? And y'all may recall that there was something called a second derivative test in a single variable calculus class. I'm going to give you a point of view on the second derivative test, a point of view that's very convenient for adaptation to the multivariable case. This might not be your favorite point of view on the second derivative test for single variable calculus. That's fine. You might just prefer to think about concavity, and it's a sort of more familiar concept. But anyway, this is adaptable, and so we're going to take this point of view. Y'all remember the second order Taylor polynomial? Right? This is, in some sense, in a very meaningful sense, this is the best quadratic, the best parabola for approximating this function f. Okay, and so the argument would begin with, well, then if this has a minimum, and this is best approximating the function, then, probably the function has a minimum too. Okay. If we're looking at a critical point means that this term is 0. Right? And it goes away. And that means that at a critical point, here's what our second order Taylor polynomial looks like. And this is a kind of a convenient polynomial. It's a convenient quadratic because what we have is a constant, which is boring. Right? That doesn't help it distinguish anything. It's all the same constant for any value of x. What's interesting is what's over here. And what you see there is a real simple quadratic. You can see the vertexes at A. Right? And this factor here is always positive. Hey, this is always positive, right? 1/2 is always positive. And so, all in all, if I want to know if this is always positive or always negative, all I have to do is look at that second derivative. So if the second derivative is positive, that means this quadratic term is always positive. That means you have an upward pointing parabola, and that means that your critical point is a minimum, right? And then vice versa if it's negative. Everybody on board? Okay, so that's a point of view on where the second derivative test in single variable calculus comes from. Like I say, this is really highly adaptable to the multivariable setting. Here's the second order Taylor polynomial for a multivariable function. And we have not talked about this before. And if you're curious where this comes from, it's not hard to motivate this. This is the unique quadratic function that has the same value as f at A, that has the same partial derivatives as f at A, and that has the same second partial derivatives as f at the point A. And you can compute all of those derivatives and partial derivatives on your own. It's a nice exercise. This function, in terms of value, derivatives, and second derivatives, is a absolute ripoff of the function f. Yes?
Is there a reason why you don't have those two x minus a's?
Yeah, there is. Yeah, it's a great good observation, and there's an important reason for that. So ultimately, I'm going to have to say, yeah, it's complicated, right? But it is just kind of a weird formula for how to write that second order term that you're asking about here. And if you sort of, I'm going to say, put them together, then you'd have x minus a dot x minus a. That's just magnitude squared. And then this second order term would be strictly a function of the distance from x to a. And it's just not how the second order term works. That's too simplified. The second order term can work in different ways. So the way this is currently constructed, you multiply x minus a first by this weird matrix called the Hessian matrix. And then you do the dot product with x minus a. This ends up being this is what the second order term looks like. Yeah. And it's just a more complicated construction. Yeah. Okay, so you can approach this kind of morally the same kind of a way. If we're at a critical point, then the gradient is equal to 0, which means that this term goes away, which means that the function is quadratically approximated by this, namely a constant, which is always boring, and therefore, really, as far as what's interesting going on, this is all we have to understand. is this sort of a this oddball, weird expression here. And if you want to know whether your critical point is a minimum or a maximum or a none of the above, you need to understand this little algebraic construction. And here's the bad news. The bad news is this is a much more complicated expression than this. This one is relatively easy to understand, and this one is not. So we're not going to have a real simple answer. There's only two cases. I mean, that's either positive or negative, both of which cases we just readily and easily understand, and nothing else to it. Sadly, this can get weird. To understand, this is called a quadratic form. To understand quadratic forms, you have to do a fairly serious amount of linear algebra. And even a little bit more of linear algebra than we typically cover in Math 216. I made sort of a challenge question in Math 216 one time where I did just that little bit more that allows for analyzing this mostly. So anyway, it's complicated. The good news is the answer is just a matter of cases. It's a weirder matter of cases, but it is still, in fact, cases. So here's how it breaks down. And this is weird. Okay, and if you'd like to see more, take Math 221. Or you can take Math 216 and talk to me in office hours, and I can fill in those blanks. So here's the first case. The determinant of that Hessian matrix might be positive. If it is, then you have a sort of a familiar story. You look at what you might loosely call a second derivative, second partial with respect to x. Positive means min, negative means max. It's just like you thought you remembered from single variable calculus. Okay, but notice that depends on, essentially, it depends on that determinant being positive. 0 is not good enough. It's got to be positive. Okay, so that's first part of the story. But again, there's other possibilities. That determinant might be negative. If the determinant is negative, game over. It doesn't matter about any of the individual second partials. That is a saddle point of some sort. I don't know what sort. It could be a Pringle. It could be a monkey saddle. No comment, right? But it is definitely not a max. And it's definitely not a min. Yeah? Okay. All right. Reminder, this term saddle point is an all-inclusive term. It refers to all sorts of not max, not min. So it includes Pringles, it includes monkey saddles, it includes shoulders. Okay. All right. Third possibility, that determinant might be 0. Right. At which point the test fails. And remember, in single variable calculus, sometimes the second derivative test fails. Right? Yes?
What if the determinant is like undefined? Like it's over 0?
If it's what now?
If it's undefined, like
then the function's not differentiable, right? So differentiability is the first condition here, right? The function's and you're right. I should have said that. So this second derivative test only applies when the function's differentiable, twice differentiable, so that everything involved is defined. Yeah, so great observation. Thank you. Right. Okay. So go ahead.
What if like the determinant of h is greater than 0, but the second partial with respect to x is also equal?
Yeah, good catch. So I left that one out. That's another failure, is the punchline. If the determinant is positive and if the second partial with respect to x is 0, then that implies, again, failure. Yep. And so we learn nothing, we know nothing. Very importantly, it does not mean that it's not a max. It doesn't mean that it's not a min, and it doesn't mean it's not a saddle point. It just doesn't mean anything. It tells us nothing. Okay. All right. So a quick application. Here's from a previous example, we have a function. We've already found the critical points, right? How do we classify these critical points? We've already agreed we don't know. The test, we can't eliminate these as possible maxes, but all we know really for sure is that they're critical points. Again, that we know nothing. Okay, so it's a matter of plugging into the test. You take this point, plug that into your Hessian. Note that Hessian, just the matrix of second derivatives. And And for this point, that Hessian determinant is positive. Right? And so that means that my test boils down to looking at that second partial. That second partial is positive. And that means I have a local min at that point. Yep. Everybody good? Okay. So that's at that point. Now let's consider this point. This point, again, plug it into the Hessian, see what you get. You get negative, game over. It's a saddle or something. It's, definitely not a max, definitely not a min. Everybody good? Okay. Alrighty. Okay, so now we're going to move on. Let me go back quite a ways here. One of the first things, really the first thing we talked about in the optimization discussion was how do you separate the two different parts of the domain. In a Calc 1 class, it's, there's an interior and there's a boundary, and the boundary is not really, doesn't require a lot of discussion. There's only 2 points. Just check them. Right? We don't need any fancy, sophisticated ways of helping us possibly reduce the number of possible of these 2 boundary points that might conceivably be a maximum. There's just 2 points. Just check them, right? And furthermore, the arguments that we applied in the interior don't apply on the boundary. So we can't deal with the boundary with algebra. We don't need to deal with the boundary with algebra. So just label them critical points and always check them. Okay. All right. But as we discussed, on the boundary, we have a much more serious problem. In the two-dimensional case, or the multi-dimensional case, we have a much bigger problem. Yeah, we don't currently have methods for how to, algebraically deal with the boundary, but now we really need methods. Now we don't have just 2 boundary points. Now we have infinitely many boundary points. Right? And I can't just check them. Takes too much time. So we're going to have to develop some ideas for how to deal with that, and it's called constrained optimization. So first of all, some terminology and sort of context. You're dealing with the unit disk. The boundary is this unit circle, and I'd like to make the observation that that unit circle is described by an equation. We call that the constraint equation. It's the equation that describes the constraint which represents the boundary that I'm interested in here. Right. Furthermore, notice that as I have it written, and very importantly, just in how I've chosen to write it in this case, we're looking at a level set of a function. That's really important. You always want to write your constraint equations as level sets of functions. The function, then, we call the constraint function. Okay. Reminder, don't forget, when you want to talk about, when you want to write an equation and be able to interpret the corresponding, what are you looking at a level set of, you got to have equals a constant, right? So don't do something silly like this. Don't write, x squared is equal to 1 minus y squared. That is not a level set of that function, right? We're not setting it equal to a constant. It's also not a level set of that function, right? So always put, all the stuff on the one side and leave at most a constant on the other side. Okay. All right, so constraint set, constraint equation, constraint function. That's the lingo. Everybody on board? Okay. Similarly, if you have the unit ball, then the boundary is the unit sphere. That's your constraint set. Here's your constraint equation, and here is your constraint function. By the way, feel free, if for whatever reason, if it comes up that your constraint equation is multiplied through uniformly by some constant, like if I were to write 3x squared plus 3y squared plus 3z squared equals 3, it's fine. Whatever, it doesn't matter. Right? The constraint function, you'll notice, would then be a different constraint function. It's fine. It doesn't matter. No problem. Oh, some people like to, for whatever reason, and this is not a problem, subtract that over to the other side of the equation and then make this the constraint function. It's fine. Cool. Doesn't matter. No problem. Any function for which you are looking at a level set is fine. Okay. Yeah. So the reason we write it like this is that the method that we're about to talk about relies, just in the way it works, on describing your set, your constraint set, as being a level set of some function. And a quick observation before we go on to the actual method: if this method simply implies that you're looking at a constraint set that is a level set of some function, notice I didn't just say the word boundary. It doesn't even have to be a boundary. Now, usually boundaries we can write like this. But if your constraint set is a plane, if your constraint set's a plane, which you describe by an equation like this, I guess that should be a D, something like that. And if you say, okay, well then here's my there's my constraint function. Yeah, cool, fine. The ideas we're about to talk about will work just fine in this case, even though it's not a boundary of something, right? So this is even more powerful of a technique than we really needed. All we were initially interested in was just boundaries. So thus the term constrained optimization. We don't want to say boundary because, hey, maybe it's not a boundary. Okay. All right. So for example, you might have a situation like this. You're trying to maximize some function. Maybe this function represents, again, think about all the econ examples of you want to maximize profit, you want to maximize revenue, you want to minimize risk, something like that. Maybe engineering examples, maybe you want to maximize efficiency, or you want to maximize power, or you want to minimize heat loss, or whatever, right? But again, you can't just go off to infinity. Realistically, there's going to be constraints on your inputs to this thing you're trying to optimize, right? You can say, well, I want to maximize profit, but you can't spend infinite money and hire infinite labor, right? There's going to be limits on what you can realistically do. Okay. All right. So, be aware of the function that you're trying to optimize. This is called the objective function. That's the function you're trying to find the max or min of, right? And then there's also completely separate function here. This, of course, is your constraint function. Right? It's very easy when you're in this optimization business to inadvertently conflate these two functions. So you got to watch out for ambiguities in not only the way you talk, but also in the way you think. Don't just think about, oh yeah, I just need to understand the gradient of the function. There's two functions. Which function are we talking about? At different stages of the process, it's different functions that play roles in specific places. Okay, so be very, very clear in your mind of the difference between the roles that these two functions play. Okay. All right. Okay, so a couple observations. First of all, notice our constraint set. For example, maybe something like this. It's got an equation. There's your constraint equation. It's a level set of the constraint function. And I just said it there. It's a level set. Your constraint set is a level set. Neat fact. The function whose level set you're looking at, its gradient is always perpendicular to that level set. And that's an old chapter 13 fact. Does everybody remember this? Gradients are always perpendicular to level sets. Right? So handy. Now first of all, does everybody remember this? By the way, if you're a little shaky on your memory of Chapter 13 and how gradients work, you definitely want to go and solidify that really well right now, as soon as possible, before because we're going to be using it very heavily in this section. Okay. All right. Okay, so let's pocket that observation. What we call the constraint gradient is always perpendicular the constraint set. Okay. All right. Now let's. What about the gradient of f? Well, what is it? F is a different function, right? F doesn't directly have to recognize any relationship with g. It's a totally different function, right? The gradient of g has got to be perpendicular, and here it is again. There's a gradient of g. It's got to be perpendicular to your constraint set. But the gradient of f, totally different function. It might point off in a totally different direction. Okay. Yeah? So what can we conclude from the gradient of f is sort of the next thing to consider. And let me remind you what we did in the unconstrained case. And we talked about this at the start of today's lecture. If you've got a non-zero gradient vector, we argued, that's telling you which direction the function's increasing. This can't be a max. Look at that. The function's increasing as I go that way. So how about this? Go that way, as indicated. Observe that the function is increasing, and then declare victory. This couldn't possibly be a maximum because, look, the function's increasing as I go in that direction. And we can't do that here because we're stuck on the constraint set, right? We're not allowed to get off of the constraint set. We're confined to the constraint set. So this, the idea that we would just fooey on that, I want to go that way, right? You can't. You're not allowed to go in the direction of the gradient. Does everybody see the issue? So, by the way, this is why we need a totally different set of rules, right? Our rule of just take the gradient, set it equal to 0. That's whatever. That doesn't apply to the boundary because we're stuck on the boundary. Okay. So here's what you can do. And by the way, in this picture, in this scenario I have pictured here, you can say, well, okay, but look, as close as possible. Yeah, I get that I'm stuck. I'm not allowed to leave this surface, this constraint set. But if I were to, drop a perpendicular, right, and go along the surface in the direction that's kind of as close as possible to the gradient of f. Yeah. In other words, make a little right triangle here like this, where that's a tangent vector. Then I'm not going exactly in the direction of the gradient, but I am going kind of and somewhat in the direction of the gradient. And couldn't I argue the function is still increasing? And as it's drawn here, yeah, totally. Here you go. There's the gradient. If you go in the direction sort of closest to the direction of the gradient, then and if the function's differentiable, keep in mind if the function's differentiable, then how fast the function is changing, namely the directional derivative. It's computed with this formula, and it's not 0. And again, as I have it drawn in this picture, I know it's not 0 because that is clearly not 0. And this is, as I have it drawn in this particular case anyway, clearly not 0. And this angle, as I have it drawn in this particular case, as relates to the cosine in that dot product, that cosine's not 0, as I have it drawn in this case. So I got a bunch of stuff that's not 0, and therefore this is not 0, and that means this function is increasing as I go that way, which I am allowed to do, right? That tangent vector is the derivative. It's the velocity of this curve in this constraint set as I move in this constraint set, right? As I go in that direction, derivative is not 0. That can't possibly be a maximum. Everybody on board? Okay. So we have to adapt the sort of, what I like to call the kind of the simple-minded, game of, how to eliminate possible maxes. We have to adapt it to the context, but this adapts very nicely, like this. Okay, and just as we did in the unconstrained case, now we have to look at where could this argument fail. I've got a tool here that should allow me to eliminate points as possible maxes. Does this always work? Can I eliminate all points? No. Right? But this is going to fail. There are assumptions that this argument relies on that, if they do not hold, then this elimination argument crashes and burns. And so there are some points where I can't eliminate it, and therefore I don't know what's going on. And again, we're going to call those critical points and, check them out in other ways at a later time. So what does this process rely on? And there's kind of three things. This relies on my being able to compute directional derivatives with that formula, which I capitalized on. So the function's got to be differentiable. Otherwise, this is an invalid argument, makes no sense, complete garbage. And my test fails and I know nothing. Right, so differentiability is the first requirement. If the function fails to be differentiable, my argument fails. Also, notice I drew this at a conspicuous tilt from the perpendicular, right? If the gradient of f were actually, if it weren't like that, if the gradient of f were like that, this argument fails because whichever direction I go, that angle's a right angle, cosine theta is 0, I would get a directional derivative of 0, which tells me nothing. Right, so that's a possibility, and the third possibility, and it's hard to draw on the picture, but it could be that the gradient of f is just a 0 vector. Right, if the gradient of f was 0, then I definitely cannot eliminate this as a possible maximum because this would fail here. All right, so three different scenarios. So you could, and I don't advise it, but you could say, hey, I'm going to say any point that has either of these properties. If my differentiability fails, if the non-perpendicularity fails, or if the non-zeroness fails. If any of these things happens, then I don't have an elimination argument. I don't know what's going on. I can't eliminate it as a possible max, and I have to call it a critical point. So you can do that. The problem is it's hard to deal with this statement right here. It's very geometric. Right? We tend to solve stuff with algebra. So can I rewrite this algebraically? And it turns out that, yeah, you can. Here's how you rewrite. You basically replace these three conditions with these three conditions, and you'll note they look pretty similar. The first observation to make is that this scenario of the gradient of f not being tilted, being perpendicular to the surface, makes it point in exactly the same direction as the gradient of g, which I'll remind you from an earlier discussion is always perpendicular to the surface. So in a happy coincidence, being perpendicular to the surface, gradient of f being perpendicular to the surface makes it parallel to your constraint gradient. So roughly speaking, we're going to replace that with this, approximately. Okay, and then some of you might wonder, so what gives? How come the gradient of f turned into gradient of g there? Why? There's a couple little subtleties here. We don't need to focus on this, but I'll just walk you through the argument very quickly. This is actually hidden inside of there. If you think about it, the case of gradient f equaling 0 would in fact make the gradient of f a multiple of the gradient of g. That multiple would just be 0, right? So I can kind of throw this away because it's automatically accounted for in that equation. So really what happens is that, what I call up here 3 prime, this 3 prime just kind of goes away. Yeah. And then, okay, well, what gives? How come we have to worry about gradient of g being 0? Well, gradient of g being 0 is something I have to worry about up here. If you think about it, where I got this from is I wanted gradient of f to be perpendicular to the surface. But if the gradient of g is 0, even if it were perpendicular to the surface, it wouldn't be non-zero vectors are not just multiples of 0. Right? So this kind of fills in a weakness of condition number 2 here. So this does not turn into that. That's not what's going on here. It's just that for separate reasons, this disappears and this completely disconnected appears for the first time. Okay. All right. So again, here's sort of the two cases that we're looking for. We're trying to understand when is our objective gradient perpendicular to the surface. And, well, if the gradient of g is non-zero, then we get that condition. But if the gradient of g is 0, that's not going to show it. So we have to consider that separately. Okay, so this is, there's a theorem. This is called Lagrange multipliers. By the way it's going to work out most of the time, vast majority of cases, you get condition 2 as the thing that finds the actual critical points for you. That this scalar here, this lambda, is called the multiplier for obvious reasons, right? And so anyway, that's the name of the method. But do be aware, this is very important. You have to check all 3 of these conditions. If you're looking to maximize a function, you can't just say, well, I found some of the critical points. I found some of the points that I have, no understanding of. And I've considered some of these points, right? If there are remaining critical points out there that you haven't even looked at, who knows? Maybe that's the maximum you were looking for. So, because of the sort of process of elimination aspect of what we're talking about here, you do have to consider all the conditions. So it can be quick. I mean, very often you just look at the function; it's clearly differentiable, and that's it. You just say f clearly differentiable, and you have successfully considered, problem 1, right? But don't forget to check this one. This is a real sticky one. A lot of students, I don't know where this comes from. A lot of students feel like, I don't feel like checking that one. By the way, this is called the degeneracy condition for reasons that we don't have time to talk about here. But don't forget to check the degeneracy condition. Right? Again, it's usually easy to do. Just go ahead and do it. And then, having done that, your study of this actually is meaningful. Okay, so example. Let's look at this question here. Want to understand that function. You'll recognize that function as being square of the distance to the origin. And subject to this constraint. Right, so I want to consider of points on this plane, which points are either possibly closest or farthest away from the origin. Right, now, obviously, on this plane extends infinitely. We're not going to find a point farthest away, right? But there is a point closest to the origin, and this point that we're looking for closest to the origin will be a critical point of this function. Okay, so your f. There's its gradient. By the way, notice this f always differentiable. There, we've just considered one of our 3 conditions, right? We got a point just for that. Don't throw away free points, right? Just write down f is always differentiable. If it is, I'm going to check and make sure that it is, right? But anyway. Okay, next we got to check and see, is our do we have a degeneracy problem? Is our constraint gradient ever equal to 0? Okay, usually, again, fairly easy to check. There, whoops, I circled the wrong thing. There is the function whose level set I'm looking at. So that's our constraint function. there's our constraint gradient, and it is easy to check that is never 0. So we've checked our degeneracy condition. See, there's nothing to it sometimes. Yeah. Okay, and so we go on to the last condition. By the way, this is I call this the Lagrange condition because this is the, again, the one that tends to be the most useful, interesting, what do you want to call it, in applying the Lagrange multiplier theorem. Okay. So there it is. We've computed the gradient of f already, and it's that. The gradient of g, again, we've already computed that, and thus that. And so this one vector equation turns into these three equations. Now, a common mistake is for students to take these three equations, run with them. The thing is, very importantly here, I'm not just looking for a random point in space that happens to satisfy the Lagrange conditions. Very importantly, I'm looking for points on this plane. Right? I'm trying to eliminate points on this plane. Any point that is not on this plane, I don't need to eliminate. I couldn't care less if I can or cannot eliminate. It's not on my plane. I am not interested in it. Right? So don't forget to add in your constraint equation. And lucky that that's there, because notice we have 1, 2, 3, 4 unknowns, and now happily we finally have 4 equations. It's hard to say, and when you're doing non-linear multivariable algebra, what will always work. And again, nonlinear multivariable algebra is really hard, but it's at least plausible, right? That you would hope that 4 equations, 4 unknowns ought to work. Okay, so this is your algebra, and it's all algebra from here. So how do you do this algebra? I can't give you a single silver bullet that will always work, but very often it goes as follows. Very often you solve for and then eliminate lambda. So notice lambda's got to equal to all 3 of these things, right? From the 3 Lagrange equations, lambda's got to equal to all 3 of these things. So if lambda's got to equal to all 3 of these things, then all 3 of these things have to equal to each other. And now, notice, there's no lambdas left. So I have eliminated lambda. Now I don't have 4 equations, 4 unknowns. Now I kind of have 3 equations with 3 unknowns. Okay, so this gives you y in terms of x. This gives you z in terms of x. Plug those into here, and you can solve for x, right? And once you know x, then you know y and z. That's how the algebra works out in this particular case. It's not always like this. It's different every time. The algebra can be weird, and oh my gosh, sometimes there's cases. My last example I'm going to show you if we have okay, technically we don't have time, but I have one more example I'd like to show you where it does break down into cases. But anyway, this is kind of roughly what it's going to go like in a very broad sense. Remember, again, usually the trick, solve for and then eliminate lambda. Okay, so time is officially up. So I would tell you what I'm going to do. I'm going to keep the recording going. If you'd like to stick around and see this last example, you're very welcome to. If you would like to take off, you're very welcome to, and I will not be offended, right? So anyway, feel free. I'm just going to keep talking, though, to show you this last example. Oh, and of course, another thing you can do is leave now and check the recording later. Feel free. It's totally fine. I don't want to hold y'all late, but I do think this last example is kind of cool. Okay. By the way, FYI, the 2 constraint case of Lagrange multipliers is not something you're responsible for. It's not super hard. It's just that, again, this course is packed, and so very often we make a decision as a course to not include the 2 constraint discussion. That is the case for this semester. You're not responsible for the two constraint story. So let's just skip over that. If you're curious, come to my office hours. I'd be very happy to talk you through this picture, etc. Okay, so I want to skip forward to this example here. It's several pages forward in the notes. We're looking on this solid ellipsoid, trying to find maxes. If you think about it, if you have a solid ellipsoid, there's actually kind of two parts to a solid ellipsoid. There's the interior and the boundary. We've talked about each of these cases. We've talked about what to do in the interior. So you got to apply that first. Take the gradient, set it equal to 0, solve for x, just like other unconstrained cases we've done. So that's an easy first consideration. And now we're left with just what happens on the boundary. And the boundary is where this inequality is an equation. So x squared plus 4y squared plus 9z squared equals 36. Right? That's that boundary. Okay, so as you'll notice then, here's your constraint function. That's your g. Right? There's your constraint gradient. We do have we have the appearance of a degenerate critical point. Something kind of interesting happens here. Again, keep in mind, any points you find, you only care about them if they're actually on your constraint set. In a seemingly sort of weird coincidence, this point that we got from looking at setting the constraint gradient equal to 0, that point is not on our boundary. And so we don't care about it. Right? This whole business about degeneracy is only as a way of helping us understand points that are on the boundary. Points that are on the boundary are all we care about at this stage. And this is not on the boundary, so toss it. Okay. So, by the way, notice that this function, of course, clearly differentiable. I forgot to write that down. Shame on me. But it's clearly differentiable, so there's no differentiability issues. Okay, so we go on to the Lagrange case, and there's your objective gradient, the gradient of the function we're trying to optimize. Here is your constraint gradient from right there, and so we have these equations. Don't forget, we're looking for solutions that are on the boundary. So we have 4 equations, 4 unknowns, and now again, off you go. Looking for the algebra. So I'm going to go now to just solving the algebra. And how do we deal with this algebra? And it's really tempting to argue as follows. So many students will do the following and say, look, that tells me lambda is equal to 1, and that tells me lambda is equal to a fourth. These two equations are in contradiction. No solutions. Pencil down, walk away. No critical points, and we don't have to do anything. Everybody see the allure of that? Right? Lambda's got to, come on, lambda's got to be 1. Look at it. Lambda's got to be a fourth. This is not possible. Right? Again, high school sloppiness. Right? I was victim of this as well. In my high school, there was all sorts of things that you can get away with, and whatever. Well, I've committed a little math crime. I've divided by something, as far as I know, could be 0. Right? So, in fact, this does not imply lambda equals 1. This implies there's 2 possibilities. Either lambda is equal to 1 or x is equal to 0. Right? That's a perfectly reasonable possibility. Everybody on board? Okay, so we got cases. Technically, you have 8 cases to consider here, right? The 8 cases being, there's 3 equations, each of which has 2 cases, and but a lot of those are directly contradictory. So anyway, you can compact the process a little bit by the following strategy. first consider what happens if x is non-zero. If x is non-zero, then yeah, for sure, lambda is equal to 1. No doubt. Right? If x is not 0, you can totally divide by it. Okay. And if lambda is equal to 1, okay, well, if lambda is equal to 1, plug that into these two equations. Y and z then would absolutely definitely have to equal to 0. Everybody on board? And if y and z are both 0, then for sure, plugging into the constraint equation, x would have to be plus or minus 6. Keep in mind our constraint equation up here. Well, anyway, here it is. It's this ellipse equation there. Okay. So that's sort of the first part of the argument. This is if x is non-zero. So if x is non-zero, then I've got right here two critical points, either 6, 0, 0 or negative 6, 0, 0. But again, that's just one case. That's just if x is non-zero. But now apply that kind of reasoning to these other cases. What if y is non-zero? What if z is non-zero? Right? And you get, well, in each case you get two more. So grand total we have here 6 critical points that we found. Right? And the only case we haven't considered is if x, y, and z are all 0. Right? We haven't considered that case yet. X, y, and z could all be 0. Oh, wait a minute. No, they can't because of this. All right, so you can break it down into these merely 3 cases here. Thus gives you 6 critical points on the boundary. Everybody on board? So you got to be really, really, really careful with this. It's so tempting to say, hey, these two equations here are in contradiction, and therefore I'm done. And if you're just that little bit sloppy with the rules of algebra, then you just missed 6 critical points. It's kind of a big deal. Everybody happy? Okay. All right. That's all I got. Enjoyed having y'all in Math 212. See y'all at the final exam a week from today, I guess. All right. Have a good one.